Alright guys, let's go ahead and review. I know it's been a while since we did chapter 5, so let's look through it here. Alright, so chapter 5 was about ions, and chapter 6 is about covalent molecules. So remember, with ions, we started off with the octet rule, and it just simply states that an atom's going to desire a full shell. And it's the full outer shell, which we call the valence shell. Remember, that's going to take 8, hence the octet for the majority of them, 8 valence electrons. Now, an ion is an atom that has gained or lost electrons. So, if you gain electrons, it is what's called a cation. So, an anion that lost electrons. A cation, think cats have paws, or the T looks like a positive. It's a positive ion, meaning an atom that lost electrons. And that's because the electrons had a negative charge. So let's say that you start with 6 positively charged protons and 6 negatively charged electrons, and you lose an electron. You'll still have 6 positively charged protons, and now you have 5 electrons, which means your resulting charge, it was 0, and now it is a 1+. Hence cation, you've lost electrons. Now an anion, remember, think a negative ion is a negatively charged ion, and that forms from an ion gaining electrons. Alright, now section 2 is when we talk about ionic bonding and salts. So I'm going to read your textbook definition of a salt just so we can remember. So it says an ionic compound that forms when a metal atom or a positive radical replaces the hydrogen of an acid. So it's going to just basically be, for example, if you have a sodium metal ion and a chloride anion, it's going to form sodium chloride, which is considered a salt. So it's a neutral compound that forms from a cation and a negative ion forming. So cation plus an anion is going to form a salt. And we think of this salt, remember that's just table salt. There are a lot of salts, and salts are going to have a few common characteristics. For one, they're all going to have something called lattice energy. And I think it makes sense more to talk about the crystal lattice first. So let's look at, for instance, if you have 1 part sodium chloride, remember you've got a sodium with a positive charge that's going to be attracted to a chloride with a negative charge. But then that's going to be on all sides. And then each of those chlorides are going to be surrounded by a sodium. And this pattern is just going to keep repeating. And how that pattern is structured is going to be dependent upon the size of these ions and the ratio of them. So since this is a 1-to-1, it's a very simple repeating lattice structure. That's going to look like this. Now 3-dimensionally, if you think about a lattice, it looks something like that. Okay, it's a ugly lattice, but you know what I mean. So a crystal lattice is the lattice that is forming from this bond. So when that sodium is bonding the chloride, it's going to make the shape of a crystal lattice when you have it repeating. And then when you have one part, so like 1 part sodium with the 1 part chloride that it's bonded to, that's called a unit cell. Okay, so that's simple ratio. So it's the smallest unit of an ionic compound. Now the crystal lattice again is the shape an ionic compound is going to take. Or form, I should say, maybe. And then lattice energy. I'm going to look up the textbook definition because I think this throws people. So it says lattice energy is the energy associated with constructing a crystal lattice, this guy, relative to the energy of all the constituent atoms separated by indefinite distance. So essentially, if you have your sodium and you're going to get that chloride and put it together and you're going to form sodium chloride, it's going to release something called lattice energy. This energy that's being released would be the energy. And that's how that lattice structure is being formed. Let's see if I can find the... let's talk a little bit about the properties of an ion. I don't think I have much here for it. Let's look here. Yeah, there isn't much here for terminology, but remember when we're talking about an ionic compound, you should also know a few things about it. For instance, you should know that ionic compounds have a few unique properties. And a lot of those are what we've been looking at in the lab the past few days. So for instance, an ionic compound is going to have a very strong bond between them. So that just means between the ions. Okay, so sodium is going to be very strongly attracted to its chloride. And that's just going to keep repeating. And so what that means is that that's going to cause the ionic compound to have a very high melting point. Because in order to melt anything, you're going to have to make that bond basically get flexible and be able to be bent and move. Another thing that we should remember about ionic compounds, so again, really high melting points, and we're talking like 1,000 degrees Celsius and higher. Okay, ionic compounds incredibly high, whereas covalent will be around the 300 to 100 and down. So another thing is that they're going to form something called, like we said, a crystalline structure. And that is, again, because of that repeating lattice structure. I think I just butchered the word lattice. No? Okay, just looks weird. And while not all crystals look the same, you can think of like a crystal point, for instance. There's going to be a lot more dimension to it than if you were talking about a crystal, salt crystal, or whatever it may be. And it's all going to be based on what ions are present and their sizes and how many of each there are. They're looking very similar to what you would picture a typical crystal to look like. The other thing we should know about an ionic compound is when melted or dissolved in water, they are able to conduct electricity. Now there's some random physical properties, for instance, like salts tend to be hard. Like we said, it's hard to break them, and that's part of it as well. Their bonds are very strong, so they're hard, but then they're also brittle. These are not opposites. Okay, brittle means once you break it, it breaks clean. Alright, so the crystal lattice definition was the regular pattern in which a crystal is arranged. Again, it's that repeating pattern that takes place. So if you were to picture it with the molecular level, I don't know that I'm going to be very good at drawing this, but you'll have we're going to have like a repeating pattern of these guys. Okay, and so that shape just keeps repeating, and that's going to make this were a 1-to-1 ratio here with sodium chloride in three-dimensional space. I'm actually going to pull a image here for you real quick. It's going to look like this. I don't know if you'll be able to see this, but it's going to have what you picture a typical crystal to look like. Alright, so there it is. So this would be calcium fluoride and this is sodium chloride. Notice they are different, but they both have those strong, it's called cleavage in terms of mineralogy, but they have those flat planes, and it breaks because when you sever this, it's going to sever clean between those spaces. So like wherever the bond is the weakest. Alright, let's make sure we haven't missed anything else. And again, unit cell was just that smallest repeating pattern. Alright, let's move on to section 3. So section 3 is just about, this is where we got our introduction into polyatomic ions. So remember, polyatomic, poly means many. So there's many atoms that form an ion. So let's look at these two, for example. They're not both ions. Okay, this guy is called ammonia. Ammonia is not an ion because there is no oxidation state or charge listed there. Whereas this is called ammonium, and it is a polyatomic ion because there's many ions and it has a charge. Now, the only time you won't see the charge listed in a polyatomic ion is if it's bonded in compound. So remember, when we have ionic compounds, you're always going to name cation, then anion. So an example of two polyatomic ions I've told you really need to learn to watch for are ammonium and hydroxide. So ammonium hydroxide is NH4 with a +1, and hydroxide is OH with a -1. Remember, when you are drawing the chemical formula for a polyatomic, it is advisable to start with parentheses and then remove them if you don't need them. Because remember the crisscross rule. This charge has a charge of 1, this has a charge of 1, so I bring it down and bring it down. Now, because I only needed one of each, I can remove those parentheses. Now, that would be your final name, chemical formula for the ammonium hydroxide. Okay, but now let's say that hydroxide were to have bonded with something like magnesium. So magnesium, not to be confused with manganese. Remember, manganese, magnesium. Magnesium has a 2+ oxidation state or charge. And if we were to pair him up with hydroxide, remember that has a 1-. Let me erase my manganese here. What's going to happen here is we are going to need to take this 2 and crisscross, take this 1 and crisscross, okay, and then I'm going to have 1 part magnesium, which I don't have to write, there's only 1, and then hydroxide will be in parentheses and a 2 on the outside. And I had to keep my parentheses here because if I had just written MgOH2, that 2 would only apply to my hydrogen. I need to tell anybody looking at it that I wanted to apply to the entire hydroxide. Because what I needed here, remember your double check for writing these guys could be just drawing them out with the oxidation states. If this is a 2 plus and one of these is a 1 minus, I'm obviously going to need two of them to get this minus this minus this to equal 0. Okay, that's the goal of an ionic compound, is to have a net charge of 0. You just keep collecting cations and anions until that net charge is 0. And the crisscross rule is just a really easy trick to get it to happen pretty simply. So let's try another one. I'm gonna grab my periodic table here to mix them up here. I think the easiest thing to forget would be the Roman numerals. So let's process a little bit about that. Naming rules mean, for naming ionic compounds, is you're always going to name the metal first. Okay, I'm going to use the example sodium chloride here just to use one we're pretty darn familiar with. So we always say sodium first. And then if metal is a transition metal, which means on your periodic table groups 3 through 12, it's even labeled on the table I've given you, then list charge in Roman numerals. If it is not a metal, I mean a transition metal, sorry. If it's not a transition metal, then you'll just say it as the elemental name. I'm out of space here. So for example, because sodium is a group 1 metal, it is not a transition metal, so we just say sodium, just like it is on the periodic table. Now that again is the cation. Now for the anion, which would be the chloride here, you're just going to simply remove the ending and add IDE. So we say sodium chloride. It normally is chlorine, but we say chloride, so sodium chloride. Remember, that's an example you can think of that you know to help you remember the rules. Now let's try think of one that would require a Roman numeral quick, so we can go back and forth. All right, so I need a brighter color so you can see better. Let's say that we have manganese, and it has bonded with fluoride, and it took 2 fluorides for this compound to form. So what you're going to do is you're going to realize that manganese is a transition metal. So you can start just by saying manganese. You know you need to put Roman numerals for the oxidation state because it's the transition metal. Manganese is number 25 on the periodic table. And then fluoride has a weird U in it. Oh, I forgot my I. It's just as it is. But what we have to do is we have to sort out what this oxidation state here is. What you can always do is look to your anion. We're always going to know the charge of our anion. We look on our periodic tables to see that fluoride falls in the group 17. Therefore, it has a 1 minus charge. But there's 2 of them. Okay, so that means fluoride with a 1 minus and fluoride with a 1 minus was satisfied with 1 manganese. So that had to have been manganese with a 2 plus. 1, 2, 2. Okay, because we need a net charge of 0. Therefore, this 2 plus needs to be spelled out in my name or whoever's reading this wouldn't know how many fluorides to pair with that manganese. Now remember, if we had to go the other way, let's say I said manganese fluoride, you would be, say, Mn and F, and then you would say that 2 means it's a 2 plus, and the fluoride is group 17, so it must be a 1 minus. My 2 comes down, my 1 comes down, and then I'm going to rewrite it. It's a 1, so I don't have to write it. F2. Okay, so that's how you go back and forth. All right, that's naming ionic compounds. Now remember, covalent is the one with the prefixes. The only tricky thing about ionic would be if you have a polyatomic called hydroxide. This always throws kids, and they think that because it says hydra and it ends in "ide", that it's just hydride. Hydroxide is OH with a -1. That's why I've told you should memorize that one so you don't miss it. All right, next, let's move on to chapter 6. Okay, chapter 6 is about covalent bonds. So remember, ionic was metal to nonmetal, or an anion and a cation, or a cation and an anion, I should say, whereas covalent are two nonmetals, two or more, we should say. So an example like carbon dioxide and carbon monoxide, a nonmetal and a nonmetal. Covalent bond is also very important to remember that the electrons are being shared, whereas ionic electrons are being transferred. Now the molecular orbit is just like if we've got H2O, remember we talked about how there are an orbital path for each atom. So like oxygen is found in the P block, so he's actually going to have this big shape where we know that the electrons have a 90% probability to exist. And hydrogen's a spherical shape, and that's where we think that electrons would exist with a 90% probability. So the molecular orbit is just like this region where we have a good, reasonable belief that the electrons would exist. So basically, the space we think this molecule takes up. All right, now bond length is pretty simple. If we have oxygen bonding to hydrogen, the bond length is the distance from the central of this atom to the central of this atom. That is your bond length. I'm going to grab the textbook definition of bond energy because I do think they say it a little funky and it can throw you. So bond energy, the textbook definition of bond length is the distance between two bonded atoms at their minimum potential energy. All right. So basically it means when he's at rest and not trying to bond or change. All right. The textbook definition of bond energy is the energy required to break the bonds in 1 mole of a chemical compound. So essentially, if you have one mole of H2O, how much energy would it take to break these guys apart? Okay, so energy required to sever the bond. A bond in a molecule. The reason I think the definition, the textbook definition, is a little challenging is because we don't really know what a mole is yet. We haven't talked too much about that. So let's just say the energy required to break a bond within a molecule is bond energy. All right, now I have this electronegativity table here because I think in order to do the next part, we need to look at this. All right, so if we are trying to figure out, and I have it on different pages, whether something is nonpolar, polar, covalent, or ionic, this is the table we're going to look at. If the difference between their electronegativities is less than 0.5, it's nonpolar. If it's less than 0.1 but more than 0.5, it's polar covalent. So both of these are considered covalent, but this one's polarized and this one is not. And if it's greater than that, it's so great, it's ionic. Okay, so polar covalent, we have a partially positive side and a partially negative side, like H2O. Whereas ionic is like sodium has a positive charge and chloride is a minus charge, so that's ionic. And then a nonpolar covalent would be like nitrogen monoxide. They're very close on the periodic table, so they are going to have very similar charges. So again, the way you find that is, let's say we were trying to figure out for H2O. You're just going to look at the value for hydrogen, and it's 2.2. And then you find the value for oxygen, and it's 3.4. And you simply take the big one minus the small one, and you only do it once. So 3.4 minus 2.2 gives you 1.2 for a value. And that should make sense because water is a very polar covalent molecule. All right, so non-polar covalent means no charged ends, meaning they're pulling on the electrons evenly. Polar covalent is one side or end or part of the molecule. Let's go part. Pulls harder on the electrons. Now dipole means one side of it's going to be positive and another end's going to be negative. And it's within a molecule or the entire molecule in general. Di means two poles is like the opposite charges. Now section 2 is drawing and naming molecules. So a valence electron again is like, say we're talking about carbon. We know carbon has 1, 2, 3, 4 valence electrons, just the outer shell. They actually have 6 total, but 4 on the outside. So this is a Lewis structure, but a Lewis structure for a bonded compound, for instance, this would be methane's Lewis structure. Remember, we start by counting how many electrons we'd work with. So if I said you have CH4, you'd say, well, carbon's going to bring 4, just like this. And each one of these hydrogen brings 1. So it's a total of 4 because there's 4 of them. And I have 8 valence electrons to work with. Now you're going to put the one you only have 1 of in the middle and surround them with the other guy, trying to make it as symmetrical as possible to start. Then you go 2, 4, 6, 8. And everybody's happy because hydrogen only needs 2. Every one of these lines represents 2 valence electrons, and carbon has 2, 4, 6, 8. So that is a Lewis structure, and these are valence electrons. Now an unshared pair is just another term for a lone pair. So if we were to draw the Lewis structure for H2O, we're going to realize that oxygen is going to bring 6 valence electrons because he's group 16, and those 2 hydrogens bring 2, so we have 8 valence electrons to work with. So there's 1 oxygen, he goes in the middle, hydrogen and hydrogen, and I've got 8, so 2, 4, hydrogens are happy, 6, 8. Now lone pairs are going to tend to want to be together, so I'm going to move them on up, and then I'm going to move this over. So these right here is a lone pair, 2 and 2. Each 2 of them represents 1 lone pair. These are bonded pairs, these are lone pairs. Now these shapes are based on the Vesper theory, so I'm going to show you that on the next one here. Bell's about to ring. All right, single bond is 1 line and it represents 2 valence electrons. Double bonds, 2 lines, represents 4 valence electrons. Triple represents 6 valence electrons. Now remember, in order for a triple bond to take place, it needs to have had the potential for 3 bonding locations. A resonance structure would be an example of a structure where the arrangement's the same, but the location of the double, single, double, or triple bonds or lone pairs are in different spots. So like say we've got oxygen surrounding sulfur, and it could be like single, but one of these has to be a double. It could have been like that, or it could have been your doubles here. Okay. And you still have sulfur. I'm not finishing this because I'm trying to rush here. Obviously, the lone pairs would also change, okay? But these would be an example of resonance structures. Just because the double bond changed and where your lone pairs are would change as well. Vesper theory members valence shell electron pair repulsion theory, and it's essentially that there are going to be different shapes based on electrons repelling each other. So this would be linear. There would be no lone pairs. Two atoms bonded to the central atom, no lone pairs. If that were to get a lone pair, or two, so let's say it's two like water, you would have a bent molecule. So linear, bent. They both have two bonded atoms, but bent has two lone pairs. Next, if you have three bonded atoms, they could be equidistant apart and flat, and we call that trigonal planar. And if it gets a lone pair, we're going to call it trigonal pyramidal.
Are you recording something?
I am.
Yeah, later.
And then the last one, if there are four like that carbon tetrahydride or methane, we're going to call it tetrahedral. Those are the shapes you need to know.